We're curve sketching without a calculator today. So remember in pre-calc when we sketched rational functions? Well, we're going to do that, but using our second derivative and our first derivative to also give us our relative mins and maxes and our points of inflection. So here we go. We're going to start with here's our recipe. Okay. One thing that we have to remember is when we check for symmetry, we're looking for even and odd functions. So when f of negative x is equal to f of x, we have an even function. And when f of negative x is equal to negative f of x, we have an odd function. Odd functions have rotational symmetry, like a cube function, about the origin. And even functions like a parabola have reflective symmetry across the y-axis. All right, remember, without a calculator. So first, we find all of our features of our function. So I'm going to go ahead and factor out the bottom of my function to give me x minus 1 squared. So I know that x cannot equal 1. And the x minus 1 squared, so I'll go ahead and rewrite this. F of x is equal to 3x minus 2 over x minus 1 squared. Nothing cancels, so I don't have any holes. So that means that the x equals 1 is a vertical asymptote. All right, so I can go ahead and sketch that in right now. Vertical asymptote at 1. Next up is our x-intercept. So again, remember we set 0 equal to the numerator, so 3x minus 2, giving me x is equal to 2/3. Our y-intercept, we plug in 0 for x, or I can take the constant of the top divided by the constant of the bottom. So I get 0, comma, negative 2. I'm going to sketch those in now. So I have an x-intercept of 2/3, comma, 0. And a y-intercept of 0, negative 2. Okay. End behaviors. So this is our Bobo-Botner eats DC, and I see that the numerator has a smaller degree than the denominator. So the denominator is growing at a faster rate of change. So on the ends, so the limit as x goes to positive or negative infinity of f of x is going to equal 0. Bobo. Bigger on bottom, 0. So on the ends, our function is going to approach 0. All right. Symmetry. We can plug in f of negative x. So I'm going to do f of negative x is equal to 3 times negative x minus 2 all over negative x squared minus 2 times negative x plus 1 gives me negative 3x minus 2 all over x squared plus x plus 1. And I am going to compare this. Is this equal to f of x? And I'm going to look. I have a problem because of the negative 3x, it's not the same sign. So I'm going to go ahead and try and factor out that negative, giving me 3x plus 2 over, and then it looks like the bottom also doesn't match. So I'm trying to see if I can get this function to equal negative f of x or f of x, and I don't think I can. So there is no symmetry that I can tell. All right, so now we want to find, because this doesn't tell us a whole lot about our graph, we're going to figure out where our relative mins and maxes are. So we're going to have to use the first derivative and the second derivative test. Okay, so the first derivative, actually it's the second derivative to find our points of inflection. And where we also can tell us our concavity. Okay, first derivative can tell us about our relative mins and maxes and our intervals of increasing and decreasing. Okay, so f prime of x is given. It is negative 3x plus 1, although you can take a derivative. over x minus 1 not squared but cubed. Now, how do we find our critical numbers? We plug in 0 for f prime of x, so negative 3x plus 1 all over x minus 1 cubed. I know that the x minus 1 cubed, when I multiply it with the 0, is going to cancel it out. So I'm just solving for 0 is equal to negative 3x plus 1, the numerator. So I get negative 3x is equal to negative 1 divided by negative 3. So x is equal to 1/3. And then I also have values, undefined values, when x is equal to 1, my function is undefined, right? So 2 critical numbers. I'm going to go ahead and graph my number line. I have f prime. I have a critical number at 1/3, a 0. And at 1, I have an asymptote. So I'm going to go ahead and graph that in. And then we test our values to see if the value is if f prime is greater than 0 or less than 0. Okay. So I'm going to go ahead and use f prime of 0 is equal to negative 3 times 0 plus 1 over 0 minus 1 cubed. I can tell that that's going to cancel. So I get a positive 1 over a negative 1 cubed, which is going to give me a negative value. So we're going to do f prime of, let's say 1/2. So negative 3 times 1/2 is equal to, or plus 1 over 1/2 minus 1 cubed. So I get negative 3 over 2 plus 1 over negative 1/2 cubed. And so I get a negative when I add those together over a negative, which is going to give me a positive. Sorry, that got a little messy. And finally, past 1, f prime of 2 is equal to negative 6 plus 1 over 2 minus 1 is 1 cubed, giving me a negative over a positive, which is going to result in a negative. So f prime is negative, positive, then negative, which tells me about f regular, which is decreasing, increasing, decreasing. So our graph is going to decrease, increase, decrease. And I have a relative min at 1/3. I have no relative max and a relative min at 1/3, comma, and we can figure that out. So f of 1/3 is, and we're going to plug it into the original function. I get 3 times 1/3 minus 2 all over, I'm going to do x minus 1 squared. So 1/3 minus 1 squared gives me, I have this all written down. Okay, that becomes 1. So 1 minus 2 is negative 1 over negative 2 over 3 squared, which gives me negative 1 over 4 over 9 multiplied by the reciprocal, 9 over 4, giving me negative 9 over 4, or negative 2.25. Okay, negative 9 over 4. Whew, we're doing this. All right, so 1/3, negative 2.25 is about right there. And I also need to find my points of inflection. So to do that, we're gonna use the second derivative, which is given. So f double prime of x is equal to 6x over x minus 1 to the 4th. Now, what do? Critical numbers. So I get 0 is equal to 6x over x minus 1 to the 4th. I see we get 6x is equal to 0, so x is equal to 0. We also have an undefined value at x is equal to 1. So when I set up my number line, f double prime, I set up 0 and 1. We have an undefined value, so I'll put a little asymptote there. Now we're going to test f double prime of, I'm going to choose -1, is equal to -6 over -2 to the 4th, which I see is going to end up being a negative. F double prime of 1/2, not 0, 1/2 is equal to half of 6 is 3 over half minus 1 is -1/2 to the 4th. That's going to give me a positive value. Positive divided by positive gives me a positive. And then we get f double prime, I'm going to choose 2, is equal to 6 times 3 is 12 over 2 minus 1 is 1 to the 4th, which also gives me a positive. Okay, what does this tell me about the graph of f? It tells me we are concave down, concave up, and concave down. I change concavity between 0 and from the left of 0 to the right of 0. So from the left of 0 to the right of 0. So right here we have a relative, a point of inflection, excuse me, at x equals 0. We need to figure out our coordinating y values. So I'm going to start with f of 0. Oh wait, we know what f of 0 is because we figured that out from our y-intercept is -2. Otherwise, you would have to plug it in. So right here, our y-intercept is also a point of inflection. All right, we're ready to graph. So we know that the graph, it is going to decrease. We will increase in this little section and decrease. We also know that it is concave down, then concave up, and concave up. All right, so this section gets close to the x-axis, and it is concave down, so it is leaning down like this. And then when I get to 0, we change to concave up. It gets close to the asymptote. Oh, it is right here is where it becomes increases at 1/3. Okay, and then from 1 onward and 1 onward, we are both decreasing and concave down. So I think it's going to look something like this. All right, and that is my best guess for our sketchy sketch. Y'all should check it on Desmos and see what it really looks like. I think we're pretty close. Okay, so now we're going to graph the next one. I want you guys to go ahead and get all the features and then before the relative min and max, and then you can check it with my work. All right, so this function, since it has a square root on the bottom, I took the inside x squared plus 2 and set it greater than or equal to 0. I solved for x, and I realized that I couldn't take the square root of a negative number, and so I know that the domain is all real numbers. Basically, I can't square any number and get a negative underneath the radical. So because the domain's all real numbers, we have no holes and no vertical asymptotes. Next, we set the numerator equal to 0. So x is equal to 0, giving me a x-intercept of 0, 0. Lastly, we're going to set the 0 equal to x to get our y-intercept, so 0 and 0. Or else I can see that I have no constant on the top, so I get 0 over the root 2, which gives me 0. And behaviors are tricky on this one. We have x over the square root of x squared, which is basically x over x. But I have to be careful because it's not, these roots are, or this function does does have the same power, but the end behaviors go to different numbers. So what I'm going to do is, as x goes to positive infinity, that's a really large number. So a positive number, it's basically positive infinity over infinity squared, and then you take the square root. So I get a positive divided by a positive. I'm just going to erase this. We get a positive divided by a positive. So what we're going to do is go to positive 1. Or let's do it like this. We're going to choose an example, a really large number, so like 100 over the square root of 100 squared. What I end up with is 100 over 100, which reduces down to 1. Okay, so we're going to do the left side, the limit as x goes to negative infinity of x over the square root of x squared. And I'm going to use an example again, negative 100. So I do negative 100 over the square root of negative 100 squared, which gives me negative 100 over 100, which goes to negative 1. So on the left-hand side, we're going to go to negative 1. And on the right-hand side, we're going to approach positive 1. We have a y-intercept and an x-intercept of 0, 0, and our domain is all real numbers. And that's all I have so far. So now we need to figure out what our relative min and our relative max is with our first derivative. Go ahead and do that, and then go. All right, so I have our derivative is 2 over the square root of the quantity x squared plus 2 cubed. And I know that there are no values that are undefined in the denominator. And I'll take the numerator, 2, and set it equal to 0. And I don't have anything, 2 does not equal 0, so I don't have a 0 either. So I have no critical numbers. Yeah, none. Okay, so what I'm going to do is just set up my number line. So the whole function is either going to increase or it's either going to decrease, because there's no point where I can change from increasing to decreasing because I have no zeros and no undefined values. So I'm just going to choose a number. I like 0. And I'm going to test that number. F prime of 0 is going to equal 2 over, let's see, 0, the square root of 2 cubed, which I can see is going to give me a positive value. So this function is always increasing, always increasing. And that also means that because we're always increasing, we have no relative mins and no, I almost wrote relative max, no relative maxes either. All right. Next up is to find you'll use the second derivative to find your points of inflection. So let's go ahead and do that now and check your work. This time, I see that nothing makes the denominator undefined. So I will set the numerator, 6x equal to 0, and I get x is equal to 0. Set up my number line, I get f double prime. I have a critical number at 0, and so I need to test to the left and to the right. All right, I substituted in negative 1, giving me negative 6 times negative 1, all over the square root of negative 1 squared plus 2 raised to the 5th power. The numerator gives me a positive value. The denominator is always going to give me a positive value. So I get a positive divided by a positive will give me a positive on the right. And then on the left, and on the right, f of 1 is negative 6 times 1, which is a negative. And the denominator is a positive, which leaves me with a negative. So what does this tell me about the graph of f? I am concave up to begin with, and then concave down. So that means I have a point of inflection at 0, 0, because I know the graph goes to the point 0, 0. So right here is our point of inflection. The graph is concave up on the left side. So concave up, so hold soup, right? Gets closer and closer to this asymptote here. Do my best. And then it becomes concave down, going to the right. And that is curve sketching.